Hello everyone, I'm Federico Danzi, a senior researcher in advanced materials at Leonardo, and today I will give you a glimpse of the use case 09 within the EECONE project. The use case 09 is focusing on green sensing electronics for structural health monitoring in composite aerostructures, and the activity is carried out by Leonardo as use case leader, together with the University of Perugia and Lunagever. Moreover, the development of some specific tasks include other project partners such as the Danish Technological Institute, Sinano and the Dassault System. Over the past decades, aircraft became a common means of long-range transportation, but not everyone is aware of how an aircraft structure is designed, manufactured and its status monitored within the operation. So traditional aircraft structures are primarily made from lightweight metal alloys whose mechanical behavior is somehow well understood. However, modern aerospace design increasingly relies on composite materials, which offer the ability to tailor the structural performance to comply with specific loading conditions, enabling lighter structure and reduced fuel consumption. Then, in the aerospace sector, the term composite structure typically refers to components made by stacking thin layers composed of high-performance resin and reinforced with long fibers with high specific stiffness and strength. And the fibers are typically made of carbon fiber and are oriented in specific direction to optimize mechanical performance. This solution, however, hinders several failure modes such as fiber failure, matrix cracking and lamination. The latter being the one of highest concern, since it's difficult to detect and it's extremely detrimental for the wall structural integrity. Considering then all of these failure modes, the certification authorities impose strict inspection check aimed at detecting any possible, let's say, flaw that would mine the wall structural integrity. And one of the alternatives that is more recently proposed by the authorities for extending this inspection time while not increasing the risk of the passengers is the use of predictive maintenance strategies that are possible only if we have a reliable sensing system that will allow us to know the health of the stracture during the operation. And one of the most relevant pieces of information that we can get from a structure is basically its strain field that is currently measuring by using strain gauges, and this is also the same technology that is used along the certification campaign of any flying component, and this implies that a considerable amount of electronics is wasted every day for the monitoring and testing of our components. Then, say that our aims within the EECONE project are: first, develop novel sensing technologies using flexible and recyclable material that could be integrated within the structures and the coupon, and that would allow us to reduce the e-waste. The second one is to explore reusable sensing technologies by investigating new adhesion process that would promote a second life for the sensing elements. And last but not least is the study of robust sparse sensor placement strategies that could be integrated within predictive maintenance algorithm while minimizing the use of electronics. We will now mainly focus on the first two and show you the preliminary results that we have achieved. Okay, so our first need was the identification of a coupon that would be at the same time easy to manufacture and test, but representative of an aeronautical structural detail that would embed a damage condition. We then decided to consider a coupon that is typically used for the certification process of any composite materials that is currently flying, and this is the so-called compression after impact sample. That is a coupon with a rectangular plane form and a thickness of a few millimeters, realized by stacking plies with different orientation. And this coupon, in compliance with the standard, is typically impacted by a drop in weight and then tested under a compressive load to evaluate its residual strength. this expected strength reduction, it's mainly related with the fact that dropping a weight compromises the coupon's integrity by promoting the generation of some failure mechanism and mainly delamination. But due to the randomness of this impact process, we then decided to skip the drop weight step, but to generate artificially the delamination in a specific location along the thickness with the predefined size by using a Teflon disc. And we can see on the left the drawing of the coupon that we designed to use. So this allows us to guarantee a sort of higher control over the test and the whole process. After, let's say, manufacturing the coupon, what we have done, we have sensorized it with off-the-shelf strain gauges and tested under compressive load in compliance with the standard. So in the center you can see basically the coupon with the sensors that are installed on the four edges together with the wiring before then being covered by sealing agents that protect it from moisture mainly. And on the right you can finally see the coupon during the test, where you can highlight a sort of bulge in the center that is basically due to the let's say fact that the compressive load it's promoting a sort of local blackening where we have placed the lamination, so that's why you see that bulge there. The reason behind this choice is the fact that first, with this sensor information, we can have a sort of benchmark of the signal that we would expect from the other sensing approaches that we will develop within the project. And second, those data will also be relevant for validating the finite elements model that will be required for the sparse sensor placement algorithm that will be introduced later on. Now, we have basically identified the material and the coupon of relevance for this investigation, and we manufacture specifically some unidirectional coupons, so basically with all the fibers having the same orientation, and this was specifically done to perform electromagnetic characterization of the substrate. This test was performed by the University of Perugia and Luna Geber to understand how this material will behave in the presence of sensors whose physical principles are mainly based on radio frequencies, and they this measurement aimed at detecting the reflection and transmission coefficient of the material, and in particular they pointed out the fact that these substrates tend to be anisotropic. Now, while this first characterization was mainly done to assess the compatibility of the material with the radio frequency based sensor, another research line has been somehow carried on toward alternative strain to the strain gauges that we currently have in operation, and that will be mainly based on similar technologies. So basically we will just find alternative again that would measure the stretch on top of the surface of our coupon by using resistive elements. So the sensors that we are currently purchasing and using, that you can see on the left from an image from a microscope, are based on a constant grid and conductive path deposited on a Kapton film, and then this sensor is basically attached on the region of interest using either Seneclert or epoxy adhesive, and at the moment those are basically single use, so we make the test and then we throw everything away, so there is no alternative. The greener alternative that we are now exploring within the EECONE are printed solution developed by DTI along the years that are based on a conductive silver path and then a carbon resistive element that is basically, let's say, printed on top of different carrier foil, Capton, PT and TPU, that will allow us to consider sort of a different type of sensors, a new type of sensor, and compare it with the solution currently in place. This is a sort of first attempt of making a comparison of printed sensor with the off-the-shelf that we are currently using, but then we also have the idea of explore even greener solution where we will, for example, replace the silver ink with the copper-based one that is currently under investigation for other use cases within the EECONE project. Moreover, as you can see in the bottom, we provided some coupons to Sinano, and basically the idea was to, the one hand, to understand the possibility of performing direct printing of the sensor directly on the substrate, so on the carbon, and on the other hand to evaluate the possibility of using graphene-based ink, so the graphene-based ink that they are developing within the EECONE project as an alternative to the resistive element of the printed sensors. The idea is then to, let's say, corroborate this study with the life cycle assessment of this traditional sensor and the new sensoring system that we are exploring within the EECONE to understand the real benefit of moving toward these new and greener solutions. This study is ongoing with the support of the SOL system that creates a specific workspace on the 3ds platform for our use case, and at the moment, let's say, due to the lack of some of the information, the comparison has been mainly based on the raw material quantities and the human activity for the material supply. But the idea is, let's say, to refine the analysis, including more and more details as much as we manage to understand exactly the source that we need to use and how to complement the data that we already have. And let's say these results are, let's say, somehow preliminary, but show already a promising reductions in terms of CO2 emission of the new configuration when we compare them with the traditional one. But let's say in any case, deeper analysis will be required. Now, moving on to the last activities that we are carried on. So basically within the use case 09, we will also give some, let's say, a trial to a sparse sensor placement strategy in order to, let's say, limit the amount of data and sensors that we will need to develop a robust predictive maintenance algorithm. Now, going a bit into the details of this approach, so the idea is basically to develop high fidelity finite element model that will mimic the mechanical behavior of the structure that we have, providing us with a sort of reliable surrogate data of the strain fields on the surface of the coupon. So as you can see here on the right top corner, it's our coupon that you have seen before during in the experimental environment with some sensors. So we have simulated the application of the load, and we have been managed to predict the delamination, initiation and propagation up to reaching a certain level of stress. And let's say the results have been compared with some data from the literature in terms of strain fields in some points where they have been measured during the experiments, and also the out-of-plane displacement in the central region of the delamination. And the results that we achieved showed a good agreement with the experiments that we found. Now, let's say once validated this model, Having this sort of numerical framework allowed us to generate a database that includes the strain field information for coupons considering different delamination position, delamination size, different stacking sequence, different thickness position of this delamination. And this results in generating a sort of big database that have been then, let's say, interpolated in a sort of fixed spatial field. This allows us to generate, let's say, coherent data sets even for simulation representing different models, let's say, different let's say, geometries or mesh. And using, let's say, this data and collecting all of them, it has been possible to identify a suitable reduced base that would allow us to make a full field reconstruction. So basically, given the database, it has been possible using the singular value decomposition and the QR pivoting to identify those that are the regions that have the maximum content of information that would be the one as the best candidate for installing our sensor in order to reproduce the full strain field of the coupon. So let's say this is briefly what we have already done within the use case 09. But now if you want to talk about what we have in mind to do next, first our idea is to evaluate the new sentencing technique that we have considered, let's say, as promising, install them and put them in a real test condition and compare the results in terms of accuracy and operational limit with the off-the-shelf solution. So this basically includes the printed solution with different inks and substrate and the radio frequency sensors, and then compare them with the off-the-shelf strain gauges. Finally, for the reusability of the sensor, the idea is then to get in contact with the partners of another European project, BIDEBA, that we have identified, and to explore the use of the adhesives developed with the bondable adhesives that have been developed within this project, to see if they are suitable for our specific application. Finally, the idea would be to, let's say, dig a bit more into the algorithm that they have developed for the sparse sensor placement and understand if it is suitable in more complex scenarios, and if it's actually, say, a useful tool to reduce the number of sensors that we have. So, said that, this is more or less what we have done and which is our idea for the use case 09, and thanks for your attention.